Alright, it's Niaki. It's Niaki osteoson. So today we are going to have the chemistry revision of the paper of May-June 2022, the theory paper from the Cambridge exam board. So here we don't mainly focus on exam board, but we try to broaden our foundation by understanding as many questions as possible from different exam boards, right? So if you're doing Cambridge, you need to understand, you need to pay attention to these instructions to candidates. So for section A, we are required to answer all the questions, and then for section B, you're only required to answer any 3 questions, right? So you need to understand the instructions if you're doing Cambridge. But if you're not doing Cambridge, what you only need to do is to pay attention to data. So we are going to have the discussions, topical discussions, exam discussions in preparation for your end of year examination. So if you happen to have any other questions, you need to message the admin so that you can discuss the questions over here for the benefit of others. So always remember to subscribe so that you'll be notified whenever we post, right? So for section A, we are starting with number 1, and the weight of section A is about 45 marks, right? So the first question says, choose from the following compounds to answer the questions. Choose from the following compounds to answer the following questions. So we have defined the term compound, right? We have defined the term element, the term molecule in our topical series. So I believe you guys, you have already visited our topical series before watching these videos, right? So first you need to attend to our topical series so that you can have the understanding and you can yield something from these revision series, right? So first you are given ammonium chloride, and then we are given barium sulfate, and then we have potassium iodide, and then we have potassium sulfide. Here is sulfate, and then here is sulfide. You need to take note of these 3, right? And you should be able to distinguish between the sulfate and the sulfide. So we have a complementary test for these 2. We're going to use a dilute acid. So this one is insoluble in dilute acid, and then this one is soluble in dilute acid, right? So you should be able to differentiate between these two anions, right? The polyvalent anions. And then we're having magnesium nitrate. So here we have this one, which is sodium ethanoate, formed by the reaction between sodium metal and ethanoic acid to give salt and hydrogen gas. So you should be able to give the products of the reaction between base and an acid, and also the reaction between an acid and a metal. So this one is the reaction between an acid and a metal to give salt and hydrogen gas. So you should be able to give the complementary test for hydrogen gas. And we also have another reaction between acid and carbonate. So for an acid and carbonate, we are going to have salt, we are going to have carbon dioxide, and then we are going to have water. And then here we're only going to have salt and water. And then this one is called the neutralization reaction. So for the neutralization reaction, you need to know the ionic equation. So this is the ionic equation for all neutralization reactions. You're going to have the proton reacting with the hydroxide ion to give water. So this is the ionic equation for all the neutralization reaction, the reaction between a base and an acid, right? And then we have this one is sodium carbonate. And for all the carbonates, you need to take note that all the carbonates are insoluble. All the carbonates are insoluble, except those for group 1 and ammonium, right? So the group 1 carbonates and the ammonium carbonates are the only one which are soluble. All the other carbonates are insoluble in water, right? You should be able to understand that. And then you also have this sodium phosphate, and you should be able to derive the formula, the ionic formula for the phosphate ion, right? So the ionic formula is PO4 minus, right? These 3. So we said when writing formulas is A to the C and then B to the D, right? These are the coefficients of the charges, right? So we're going to have A, D. So this is the chemical formula. So the charge of B is D, right? So D is here. So here the charge of the phosphate ion is 3, as you can see. So you can easily relate using this format, right? And then we have zinc sulfate, right? So we are required, each compound may be used once, more than once, or not at all, right? So state which compound reacts with dilute nitric acid to form a gas that turns lime water milky. So a gas which turns lime water milky is carbon carbon dioxide. So this is the confirmatory test for carbon dioxide, right? So we want to have the reaction. So we said here the reaction between an acid and a carbonate is going to give us salt, carbon dioxide, and then water, right? So we want a reaction of a carbonate with nitric acid. So we are going to find the carbonate. So our carbonate is sodium carbonate. So sodium carbonate will react with nitric acid to give sodium nitrate and to give carbon dioxide in water, right? As simple as that. So we are going to be having sodium carbonate here, right? And then we proceed to the next part. So the next equation says react with warm water, warm aqueous sodium hydroxide to form a gas that turns damp red litmus paper blue. So a gas which turns damp red litmus paper blue, we're having ammonia. So chlorine turns the blue litmus paper red. Chlorine turns blue litmus paper red, right? Chlorine gas. And it also bleaches the litmus paper. So we want to have a reaction which is going to produce ammonia, right? After warming with sodium hydroxide. So the reaction is going to be between sodium hydroxide and ammonium chloride. So ammonium chloride will react with sodium hydroxide. So the reaction between ammonium chloride and sodium chloride, you're going to have ammonium chloride plus sodium hydroxide. We are going to have sodium chloride plus ammonia plus water. So these are the products for the reaction. So we are going to have the ammonia gas, which is going to turn the red litmus paper blue, right? It's a basic gas, right? So we're going to have ammonium chloride here. And then we go on to part C, which says the compound which reacts with diluted hydrochloric acid to give a gas that decolorizes acidified potassium permanganate, right? So we want to produce a reducing agent, right? So this one is our oxidizing agent. So we defined an oxidizing agent as a one which becomes reduced after the end of the reaction, and the reducing agent is the one which becomes oxidized after the reaction. So we want to have the one which is going to have to produce sulfur dioxide, which is a reducing agent, right? So only the sulfite, they are the one which are soluble in the acidic medium. So they will react to produce sulfur dioxide, right? So we are going to have potassium sulfite. So it's potassium sulfite, right? And then we go on to the next equation, the compound which is prepared using precipitation reaction. So for precipitation, we are mixing two liquids. So it's aqueous plus aqueous to give us a solid plus aqueous. So this is the first law of a precipitation reaction. We are going to mix two liquids, aqueous mediums, to obtain a solid precipitate, which will then float in the aqueous medium, right? So this is the general law for the precipitation reaction. So which one is going to precipitate? So we are going to have a barium sulfate, right? So the barium sulfate, we're going to mix, for example, barium chloride plus sodium sulfate, right? So we are going to mix these two aqueous solutions. So it's barium chloride, and we are going to have sodium chloride plus barium sulfate. You can balance the equation as simple as that. So we can easily balance the equation by having a 2 here, right? So the compound here which you can be formed using precipitation reaction, we are having barium sulfate. And we now proceed to the next part, which says a compound which contains an ion with a charge of -3. So we have alluded to that before when we derived the ionic formula for the phosphate ion, which is PO43-. So it is a sodium phosphate, right? So we are having sodium phosphate, as simple as that. And then the compound which is used to test for an oxidizing agent. So for a compound which can be used to test for an oxidizing agent, we are going to have so from the list, we are going to have potassium iodide, which can be used to test the presence of other halogens, for example the chloride, the bromide, and the fluoride ion, right? So we can use potassium iodide. So, and also we can use this one in the test for starch, right, where we are going to observe a blue-black color, right? So we are going to use potassium iodide, right? And we can now proceed to the next equation. So the next question says, the table shows some information about the elements in group 5. So for group 5, you are starting with nitrogen, going on to phosphorus and etc. Right? So these are the elements. So we are having nitrogen, phosphorus, arsenic, antimony, and bismuth. Right? So these are the elements in the group 5. Right? So here we have the electronic configuration. We defined electronic configuration is the arrangement of electrons in their electric shells, right? And then we have melting point, we have boiling points. Alright, so state the electronic configuration for phosphorus. So we say the first shell is filled. So phosphorus is on number 15 of the periodic table, right? Meaning to say for a neutral atom, the number of electrons is equal to the number of protons, right? The number of electrons is equal to the number of protons. So if you are to have 15 as the atomic number, it simply means to say we are going to have 15 electrons. So we say the first shell is filled with 2 electrons, right? And then all the other shells are going to be filled with 8 electrons. So we don't fill the next shell if you are not having, or if you haven't attained maximum occupancy, if you are not having 8 electrons in the outermost shell, right? So we are going to have 8, and we have now used 12. We have now used the 10 electrons, and then from 15, when we use the 10, we are left with 5. So it's going to be 5 here, right? So this is the electronic configuration for phosphorus. And then we go on to the next equation. So the next equation says, explain why it is easier to predict the boiling point of bismuth than to predict its melting point. So we need to have the understanding of this trend. So from nitrogen to phosphorus, we have an increment, right? And then from this one, we have a steep increase in the melting point, and then here we have a decrease again, right? So you need to understand that we are not having a defined trend in melting point, right? This trend is not defined. But here for the boiling point, we are having minus 196 to 280, and then from 280 to 618, and then from 618 to 1380. So we have an increment in the boiling point as we go down the group. So this is a defined trend. Boiling point increase with increase in the molecular size. Why? Because we are having stronger intermolecular forces, what you call the Van der Waals forces, right? So we explained that in the topical series where we said the increment in the mass, or the factors governing the physical properties, are what you call the intermolecular forces, right? So intermolecular forces, these are the forces which are held the molecules or the particles in the lattice structure. So these are the forces. The strength of these forces is what governs the boiling point. So if you are having stronger forces, we are also going to have a great amount of energy which is required to separate the molecules during boiling, right? So we have a defined trend for boiling, and we don't have a defined trend for melting points. That's why it is easier to predict boiling point than to predict melting point. As simple as that. And we go on to number C. So number C says, use the information from the table to explain why antimony is a liquid at 1000 degrees Celsius, right? So the melting point of antimony is about 630 degrees Celsius, and the boiling point is 1380 degrees Celsius. And the question says, at 1000, confirm that at 1000 degrees Celsius it is a liquid. So the melting point is 630, and the boiling point is 1380. So this simply means to say at 1000 degrees, which is between these 2 points, right? At 1000 we are going to have a temperature between these 2 points. This simply means to say we are going to have antimony as a liquid. As simple as that. So this 630 and below, it is the solid phase, and then 1380 and above, it is the gaseous phase. Meaning to say this in between is what we call the liquid phase, right? So we have done that, and we go on to the next part, which says nitrogen exists as a diatomic molecule. Draw a dot and cross diagram to show the bonding in nitrogen. So nitrogen is in group 5, so it's 2, 5, right? So for nitrogen, we are going to have a nitrogen to nitrogen triple bond of a bond energy of about 945 kilojoules per mole, right? And so we are going to have this one. So we are only going to draw the valence shells, the outer shells, right? And we represent these electrons. So we're going to have the dot from the other nitrogen, and then this cross from the other nitrogen, right? So this is for you to understand, right? So if you are to have 1 electron, this one is going to give us 1, 1, 1, 1, 1, right? So for this one, we have used 3 electrons, and we are having 5 in the outermost shell. So this simply means to say we are left with 2, right? So we are going to have 2 here, and then 2 there. So the total electrons, we're going to have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this one, all the nitrogen atoms have attained the stable noble gas electronic configuration, right? They have attained stability. And then we move on to the next part, which says explain in terms of structure and bonding why nitrogen has a low melting point. Explain in structure and bonding. Why nitrogen has got a low melting point. So we said the intermolecular forces are what governs the melting and the boiling point and all the physical properties. So if we are having low melting points, this simply means to say the forces holding the molecules together are weak. So we have weak forces. Why? So these are what you call the van der Waals forces, the instantaneous dipole moments, right? So these forces are weaker in the nitrogen atom. So they increase with increase in the molecular size. So as you can see from this diagram, from this step, so there's increase in the boiling as we go down the group. So the forces increases with increase in the molecular size, right? So as we move from nitrogen to phosphorus, we're having an increment. From this one to this one, you're having an increment. So they increase with increase in the molecular size, right? So the van der Waals forces, or the instantaneous dipole moments, they are going to increase with increase in molecular size. So from nitrogen, is a smaller molecule, meaning to say we are having weaker forces. That's why we are going to have a low melting point. It's same with that. And then we go on to number E. So number E says bismuth is a metal. State 2 properties of bismuth. So they are first telling us that it is a metal. So, and we are required to give the 2 physical properties. So if you are required to give the physical properties, they're only requiring you to give the physical properties for a metal. So what do we know for a metal? What are the physical properties of a metal? So one of the physical properties of a metal, it is a good conductor of electricity, right? And it also conducts heat. Good conductor of electricity, good conductor of heat. It is also malleable, ductility, and high density, right? So we have good conductor of electricity and heat, and also malleability, and also ductility, right? And also high density, and etc., right? So these are the properties we are going to give. And then number F says calculate the volume in cubic decimeters of 19.2 grams of nitrogen at room temperature and pressure, right? So we want to calculate the volume in cubic decimeters of 19.2 grams of nitrogen. So nitrogen exists as a diatomic. So this is nitrogen. So we're going to have the mass. So the mass for single nitrogen atom, it is 14. So if we are having 2, we are going to have 14 by 2 to give us 28, right? So we are saying that it's RTP. So the volume of a gas at RTP depends with your example. So for Cambridge, it is 24 cubic decimeters, right? So we are going to say 28 is going to give us 24 cubic decimeters. 19.2 is going to give us less, and we are going to simply carry out the proportion. So we're going to have 19 over 2 over 28 all over 24, and we are going to punch this straight to our calculator, right? And we are going to obtain 16. So we are going to have 16.457. But the question says 2 significant figures. So this is now the mathematical application, right? So we are going to have, this one is the first, this one is the second. So we want to round to this second significant figure. So we're going to have 16. As simple as that. And we go on to the next equation. So the next equation says the diagram shows some of the reactions of butanol, right? So we have this is the butanol. So butanol, from this suffix, we can understand that it is an alcohol right? So the functional group is an alcohol. So this is organic chemistry, right? So we have butanol, which contains 4 carbon atoms, right? So we have this hydroxyl group, which is the functional group, right? So this is the homologous series of alcohols. So when we are further classifying these alcohols, we can say this one is a primary alcohol, right? So we are going to have the reaction of incomplete combustion. We have the reaction of complete combustion. We have the reaction with acidified potassium permanganate, and we have the reaction with ethanoic acid. And then we are given these are the products. These are the products we are going to have, right? And then the question says A, B, C are different compounds. Identify A, B, and C, right? So the reaction where we are having complete combustion, we are obviously going to have carbon dioxide and water. Carbon dioxide and water for complete combustion. And if we are to have incomplete combustion, if we are to have incomplete combustion, we are going to have water with either carbon monoxide or soot, right? So these are the products of incomplete combustion. We're going to have either carbon monoxide or soot. And we go on with ethanoic acid. So this is what we call esterification, right? Esterification, the manufacturing of esters, right? So esterification, we are going to have the reaction between an alcohol and an acid, organic acid, right? So esterification, it is an organic reaction, right? So we are going to have the liquid B. So liquid B, it is water, and then the organic, it is the ester, right? Butyl ethanoate. Are we together? Ethanoate, as simple as that. And then the reaction in the presence of acidified potassium permanganate, we're going to oxidize. So this one is an oxidizing agent. We're going to oxidize this functional group to form what we call in carboxylic acid. So we are going to have butanoic acid, right? Butanoic acid, as simple as that. So the question says identify A. So where is our A? So A, we said it is carbon dioxide, right? So gas A, carbon dioxide. And then B, where is our B? So B, the liquid B. So we said B, it is water, right? And then C, where is our C? We are either to have soot or carbon monoxide, right? So it says gas, meaning to say we are going to have carbon monoxide. As simple as that. And then we go on to B. Name and draw the structure D. So D, we said it is butanoic acid, right? So we said it is butanoic acid. So it is butanoic acid. And then for the structure of butanoic acid, but means 4 carbon atoms, right? So we are going to have 1, 2, 3, 4, right? As simple as that. And we are now giving these hydrogen atoms, right? And we go on to C. Name and draw the structure E. So for the structure E, we say it is an ester butyl ethanoate, right? So we say it is butyl ethanoate. As simple as that. So for the structure, we are simply going to have C, and we are going to have this ester linkage, and we are going to have this butyl group, right? 1, 2, 3, 4, right? As simple as that. And we are done, right? And we now move on to the next part of the question, which is number 4. So number 4 says the table shows the information about some properties, some particles, I mean. So we have this chlorine, and then we have this chloride ion, we have potassium, and then we have this potassium ion, right? So these are the proton number and the nucleon number. All right. So the nucleon number is defined as the sum total of protons and nucleons in the nucleus, right? So we did atomic structures. So you should go and check on our playlist, right? So the proton number is the number of protons in an atom, right? So state the number of neutrons in chlorine, right? So chlorine, we said, so from the nucleate notation, this one is the mass number, and then this one is the number of protons, right? So we said nucleon number is also equal to mass number. So nucleon number N is equal to protons plus neutrons, right? So let us say it's N naught, right? So that we can differentiate between the two. So N naught is 35 is equal to P, the proton number 17, plus N, the unknown, the number of neutrons. So it's 35 minus 17 to give us N, right? So we can simply go straight to our calculator. 35 minus 17, we are going to have 18 here. Are we together? And we are now moving on to the next part. of the equation. State the number of electrons in the chloride ion. So this negative sign indicates that we have gained an extra negative center, which is the electrons. So we said electrons are negatively charged, and then protons are positively charged, and then the neutrons, there doesn't have any charge. So this negative indicates that we have gained an extra negative center. And then the number here, the coefficient of this negative sign, indicates the number of electrons we have gained. So if we are having 1, it simply means to say we are going to have 1 electrons in extra, right? So chlorine atom, the number of protons is equal to the number of electrons, right? So for this chloride ion, the number of protons is no longer equal to the number of electrons. This simply means to say we are going to have an increment or a decrement in the number of electrons. So in the case of this ion, we are going to have an increment. Why? Because we have gained an extra negative center. So we are simply going to add 1 to this number, right? The number of electrons in the neutral atom. So we are simply going to say 17 plus 1 to give us 18. Are we together? It's simple as that. And we go on to the next part, which says potassium is the full symbol for one isotope. So this one is the full symbol for one isotope of potassium. So we defined isotope as atoms of the same element with the same number of protons, same number of electrons, but different number of neutrons. Right? So this simply means to say they are going to have different nucleon number. Why? Because this number of neutrons will affect this number, right? So the mass number is going to be different since the nucleon number is equal to mass number. So we have discussed this in the topic of series. We have discussed this in its full depth in the topic of series. So you should go and watch our tutorial so that this can solidify in your mind, right? So suggest a full symbol for the other isotope of potassium, right? So the other isotope of potassium, so we are only going to change where we are having the mass number, right? So we said from the definition the number of protons is the same, right? So we are only going to change here where we are having the mass number. So here we are having 39, so it's either we are going to have 40 or we are going to have 41, right? Or we are going to have 42 and etc. So the number should be reasonable, right? So the number should be reasonable, right? And then we go on to the next part, which says describe how a potassium ion is formed from a potassium ion atom. So the formation of this ion, so this one is a cation, a positively charged ion. This one is a cation. So cations are produced by the when atoms they are going to lose the electrons. So we say the number of protons is equal to the number of electrons. So if you are to lose electrons which are negatively charged, you are going to be left with more positive centers. That's why we are having a positive sign here. So this indicates that we have lost an electron, right? This positive sign. Are we together? So the formation, potassium is going to lose electrons. How many electrons are we going to lose? The coefficient of this charge tells us the number of electrons we are going to lose. So potassium is going to lose one electron. As simple as that. And we go next to the question which says potassium chloride is an ionic compound. So we explained ionic compounds in their full depth in the bonding series, right? So you should go and have that discussion behind the back of your mind, right? You should understand that discussion by heart because it is one of the fundamentals in the world of chemistry. So potassium chloride is a high melting point and high boiling point. Explain why potassium chloride have got a high melting point. So we said the physical properties are governed by the forces, the intermolecular forces holding the lattice structure. This is the starting point for each and every explanation for the physical properties. We first identify the intermolecular forces, right? So first we need to identify the intermolecular forces, and then our definition or our explanation is derived from the intermolecular forces. So if we are to have strong intermolecular forces, we are going to have a high melting and a high boiling point. And if we are to have weak forces, we are going to have a low melting point. We are going to have a low melting point and a low boiling point. As simple as that. So here we're having a high melting point. This simply means to say we're going to have stronger forces holding the particles. So you can then identify the forces, right? So these are what you call the strong electrostatic force of attraction between the cation and the anion, right? So we have what you call the electrostatic forces of attraction between the particles, of attraction between the particles. So these are the forces which are holding up the particles together, right? So we go on to the next part of the question, which says predict two other physical properties of potassium chloride. So any compound, they are brittle, they don't conduct electricity, solid form, they only conduct electricity in aqueous or in molten phase. And high melting, high boiling point. What else do we have? Dissolves in water. We have what you call the solvation, enthalpy change of hydration, and enthalpy change of solution, right? So you should be able to give the physical properties these compounds in relation to the bonding, right? So we are now moving on to the next part. So the next part, which is number 5. So number 5 says the ion reacts with steam and dilute sulfuric acid. Ion reacts with steam and dilute sulfuric acid. The reaction between ion and steam is reversible. So whenever we are dealing with reversible reactions, what should come first in your mind is the Le Chatelier's principle. So the Le Chatelier's principle is what governs all the dynamic equilibrium reactions, right? So a reversible reaction is defined as a reaction which can proceed in either directions. So we explain this in our topical series. So you need to go and have a look on the high yield topical series, right? Because this topical series, they are designed, so these topical series are designed based on the exam questions. So you should go and have a look on them. So this is the reaction, and we are told that it is an exothermic reaction, meaning to say it releases heat to the surrounding, or the energy content for the products is less than the energy content for the reactant, is simplified with this energy profile diagram. These are the products, these are the reactants, activation energy. So here is our activation energy, and then here is our enthalpy. So you should be able to draw energy profile diagram, right? In terms of energetics, chemical energetics. Are we together? So an equilibrium mixture is formed when a reversible reaction happens in a closed system. So you should take note that for an equilibrium mixture to form, we need a closed system, right? So the first part says predict what happens to the amount of hydrogen in the equilibrium mixture if the temperature is increased and the pressure remains constant. So this one is an exothermic reaction, right? And then we are told that we are going to increase temperature. So this forward reaction is an exothermic reaction. So if we are to increase temperature, we're going to favor this endothermic direction so that we can reduce the effect of temperature, right? So this we're going to favor this backward reaction, thereby decreasing the concentration or the amount of hydrogen, right? So first we need to understand the Le Chatelier's principle. We need to understand the Le Chatelier's principle. So this it is the fundamental concept which governs all the reversible reactions, all the dynamic equilibrium reactions, right? So we are saying that according to Le Chatelier's principle, an increase in temperature will favor this endothermic reaction, which is the backward reaction, thereby reducing the concentration of hydrogen. So the prediction, the amount of hydrogen is going to decrease. Why? Because we are going to favor the endothermic reaction, trying to absorb heat or to reduce temperature. As simple as that. And then we go on to the next part, which says predict what happens to the amount of hydrogen again in the equilibrium mixture if pressure is increased and temperature remains constant. So the effect of pressure is notable only in gases. So we need to take note on the gases only, right? So let me clear this one so that we can easily identify the gases. So this one is in solid phase, so we cancel this out. This one is in gaseous phase, right? This one is in solid phase, so this one we also cancel this one out. And then the number of moles for gases. So here on the reactant side, we are having 4 moles, and then here on the product side, we are also having 4 moles for the gaseous phase, right? So the number of moles on both sides of the equations, they are equal. So the effect of pressure is not appreciable, is not notable. So there is no effect on the equilibrium position, right? So prediction, no change, right? No change. Why? Because we are having equal number of moles of gases on both sides. So for the in terms of equilibrium position, when dealing with gases, you need to first take note of the state and also to compare the number of moles. If you are having this equal number of moles, the effect of pressure will cancel out, right? And then we now proceed to the next part, which says iron reacts with dilute sulfuric acid to make aqueous iron sulfate. So this is iron sulfate. And then construct the ionic equation with state symbols for this reaction. Construct ionic equation with state symbols for this reaction. So we are having the reaction between iron plus dilute sulfuric acid. So this is the sulfuric acid, right? And then this is going to give us iron 2 sulfate. So it's iron 2 sulfate. So this is the reaction between metal and acid. So we're going to have hydrogen gas, right? So for the ionic equation, so this one is in aqueous phase, this one is in solid phase, this one is in aqueous phase, and then this one is in gaseous phase. So for the ionic equation, we then split the ions in the aqueous phase, right? So we're going to have ion in the solid phase plus 2 protons plus the sulfate ion in the aqueous to give iron 2 aqueous plus the sulfate 2 in the aqueous plus hydrogen gas, right? So we then cancel the ions which are common on both sides of the equation. So we have ion, so ion is not an ion. We have proton, so here we are not having any proton, and then we have the sulfate, here we are having the sulfate. So this one is going to cancel out, and we are going to be left with ion in the solid phase plus 2 protons or hydrogen ions to give us in the aqueous, to give the ion 2 in the aqueous plus hydrogen in the gaseous phase. As simple as that. And then describe a chemical test to confirm that iron 2 sulfate is formed instead of iron 3. So we are being examined on the confirmatory test to distinguish between iron 3 and iron 2. So if you are to add sodium hydroxide, aqueous sodium hydroxide, and then warm, iron 2 is going to give us a green precipitate, right? And then iron 3 is going to give us a brown precipitate. As simple as that. So first you need to know the chemical reagent and then the expected results. Are we together? And then we now move on to the next part of the question. So which is number 3 in Roman numerals. So the question says aqueous iron 2 sulfate formed is crystallized to make hydrated iron 2 sulfate. So this is the hydrated salt. So this is what we call the water crystallization, which is the water bonded to a solid or an ionic compound in the lattice structure. So the question says calculate the relative formula mass for the hydrated ion. Calculate the relative formula mass for the hydrated iron 2 sulfate, right? So we are going to simply add the relative atomic masses of each of these ones, right? So for iron on the periodic table, the mass, the AR of iron, we are going to have 56, and then we have 1 sulfur. So for sulfur we are going to have 32, and then we have 4 oxygen. So for oxygen is 16, so we are going to have 16 by 4, and then we have water. So for water is 18, right? So it's 7 by 18, and then we simply go straight to our calculator, and we are going to have 278. As simple as that, right? And then we now proceed to the next part, which says a student uses 2.8 grams of iron to make 12.5 grams of hydrated iron 2 sulfate crystals, and then this is 90% yield. And then the question says calculate the mass of hydrated iron 2 sulfate crystals made from 2.8 grams of iron if the yield is 100%. We are told that 90% we are going to have a yield of 12.5, right? So it's 90 is going to give us 12.5. So what is the expected outcome from 100%? So it is obviously going to be more. So we are simply going to say 100 over 90 multiplied by 12.5. So this is simple proportion, right? So we go straight to our calculator and punch this, and this is going to give us this is going to give us 13.9 grams, right? And then we go on to the next part, which says aqueous iron 2 sulfate is electrolyzed using graphite electrodes. So you should be able to define the term electrolysis and also to define the term electrodes and to give the properties of electrodes. So electrodes should be innate and also they should be able to conduct electric current, right? So predict the products of this electrolysis. So we are using aqueous. So first you need to identify the cations and then the anions. So for the cations we are going to have ion 2, and then the proton. And for the anions we are going to have the hydroxide ion and then the sulfate ion. So we go straight to the reactivity series. So this one is more stable than this one, so we are going to discharge the proton. We are going to reduce the proton to hydrogen gas, right? So we are going to have this reaction plus the electron to give hydrogen gas. So 2 here, then a 2 here, gas here, and then aqueous here. Are we together? So this is what you need to understand for the cathode. And then for the anode, we are going to oxidize this hydroxide ion. So this hydroxide ion is going to be oxidized into oxygen plus water, and then we can balance here with 4 and then here with 2, and we are going to also have 4 electrons here. So it's 2 and then 2 here. So the equation is now balanced. So you're going to have oxygen gas as the anode, right? So we define anode as the electrode where we are having oxidation, and then cathode is the electrode where we are having reduction and then oxidation, right? So we have the mnemonic red kit, and then here we have this one in wax. As simple as that. And then we go on to the next part, which says iron is extracted from the iron ore in the blast furnace. Describe the essential reactions involved in the extraction of iron. So this is awarded for 3 marks. So first we have the reaction of coke, combustion of coke, right? Combustion of coke. So this is one, we're going to have coke with carbon to give carbon dioxide, and then we are going to reduce carbon dioxide by reacting it with carbon to give carbon monoxide, right? And then to balance this equation we need a 2 here, and we are going to reduce the iron ore. So the iron ore is iron 3 oxide plus 3 moles of carbon monoxide to give iron plus 3 moles of carbon dioxide, right? So to balance this equation we need a 2 here, right? So this is the main reaction, right? And then we also have the decomposition of limestone, which is calcium carbonate. So this is the chemical formula for limestone, calcium carbonate. So it is going to decompose to give calcium oxide plus carbon dioxide. When we have the use of calcium oxide to remove the impurities, so it's calcium oxide plus silicon dioxide to give calcium silicate, which is slag. Are we together? So these are the chemical equations, right? So we proceed to section B. We are now on section B. So section B, we are required to answer any three equations. So section B says carbon monoxide and nitrogen monoxide. Carbon monoxide and nitrogen monoxide are pollutants formed in the car engine. Describe how nitrogen monoxide is formed in the car engine, right? So at high temperatures in the car engine, nitrogen and oxygen are going to react, right? So this is the simple explanation we are going to have. So at high temperatures we are going to have the reaction between nitrogen gas plus oxygen gas to give nitrogen dioxide gas. So this is what happens, right? And then carbon monoxide reacts with nitrogen monoxide is shown. So this is the equation and we are going to have this reaction is extremely slow at room temperature, but it is faster in the presence of a catalyst in a catalytic converter. So you need also to define the term a catalyst, right? So a catalytic converter, it is one which reduces the concentration of these harmful oxides by the use of the enzyme palladium. We have palladium, we have platinum, and we have rhodium, right? So these are the catalysts we are going to have in the catalytic converter. You should also be able to give the equations in the catalytic converters. All right, so explain why this reaction involves both oxidation and reduction. So these are what we call the redox reaction, where we are going to have both oxidation and reduction. So first, for oxidation, as you can see, carbon monoxide is being oxidized to carbon dioxide by the gaining of an extra oxygen. Here we are having one oxygen atom, here we are having two oxygen atoms, right? So we can define oxidation in terms of gaining of electrons, and we can also define oxidation in terms of oxidation charges, oxidation states, I mean. So here the oxidation state for oxygen is 2 minus, and that one for carbon X. So it's X minus 2 is equal to 0, so X is equal to plus 2, and then here is minus 2, and then X, so it's X minus 2 by 4 plus minus 2 by 4 to give us 0. So X is equal to minus to plus 4, I mean. So this is an increment from plus 2 to minus to plus 4, I mean. So this is an increment in the oxidation state, right? And then in terms of reduction, nitrogen has lost its oxygen to give nitrogen gas. So this is reduction, the loss of oxygen, and we can also define it in the terms of oxidation state. So this one is 0, and then from this one we have minus 2, and then X. So it's X minus 2 is equal to 0, X is equal to plus 2. So from plus 2 to 0, we are having a decrement in the oxidation state, right? And then we now proceed to the next part, which says the reaction between carbon monoxide and nitrogen monoxide is an exothermic reaction. Explain using the idea about bond breaking and bond forming why the reaction is exothermic, right? So the energy released when new bonds are formed is greater than the energy required to break the old bonds, right? So the energy released when the new are formed is greater than the energy required to break the old bonds. As simple as that, right? And then we now proceed to the next question. Explain using the idea of particles why increasing temperature increases the rate of a reaction between carbon monoxide and nitrogen monoxide. So the effect of pressure of temperature, we have the increment in the molecular kinetic energy, and we also have the increment in the energy content of the particle, right? So for the reaction to occur, we must have the particles colliding in the correct orientation with sufficient energy. So the increase in the kinetic energy, the particles are going to increase in the rate of collisions, and then increase in the energy content, the particles, they are going to have greater energy for the collisions, right? And then we now proceed to the next equation. So the next equation says explain why a catalyst increases the rate of a reaction between carbon monoxide and nitrogen monoxide. So a catalyst provides an alternative route with lower activation energy, right? Activation energy defined as the minimum amount of energy required to start a chemical reaction. So a catalyst is going to provide an alternative route, right? An alternative route with lower activation energy, right? So the reaction is going to occur at a lower energy cost, right? And then explain using ideas about particles why a catalyst in the catalytic converter needs to have a surface area. So for a surface area, the molecules are going to adsorb on the surface. Thereby we are going to increase the rate of the collisions, and then the reaction is going to occur since we have increased the surface area, right? So we are going to increase what you call the contact points, right? So we are going to have an increment in the contact points by increasing surface area, right? And then thereby we are going to have increase in the rate of collisions, and then we are also going to increase effective collisions, thereby increasing the rate of the reaction. As simple as that. And then we can now proceed to the next part, which is number 7. So number 7 says aluminium is an element in group 3 of the periodic table. Aluminium is used to make containers of food because it doesn't react with water. In other words, we are saying it resists corrosion, right? It resists corrosion, right? So we are going to explain this when we are dealing with what we call A-level chemistry in terms of periodicity, right? So state and explain in terms of properties on other larger scale uses of aluminium, right? So other uses of aluminium, we are going to have the manufacturing of overhead electric cables, overhead electricity cables, right? Or pipeline or power lines, I mean. So why? Because aluminium, it is a good conductor of electricity, and also it has got a lower density, right? Lower density, making the cables light. Lower density, making the cables light, right? And then we go on to the next question, which says explain why aluminium doesn't react with cold water, right? So cold water forms an impervious layer of aluminium oxide which resists further reaction, right? So we have the formation of a thin layer of aluminium oxide. So this layer is going to prevent further reaction, right? So this layer is going to prevent further reaction. Why? Because it is impermeable layer. So it prevents water from reaching the underlying metal, right? So this is the explanation. And we go on to number C, which says describe with the aid of a label diagram to show the bonding in the solid aluminium. So aluminium, it is a metal, so which means to say we have metallic bonding. So we have alternating cations lying in the sea of delocalized electrons, right? So aluminium is in group 3. It simply means to say it is going to lose 3 electrons. That's why we are having 3 plus. So here we are having electrons. So you should indicate the charge for the electrons, right? So electrons are negatively charged, as you can see, right? And then for the explanation, metallic bond consists of the positively charged aluminum ions, which are the cations, arranged in a regular pattern among the electrons, right? So we are having the metal aluminum ion, which is the cation, and then alternating between the electrons. So there is regular pattern in the scene of delocalized electrons, right? Are we together? And then we now move on to D. Aluminium is manufactured by the electrolysis of aluminium oxide dissolved in molten cryolite, right? So aluminium is manufactured from the ore, which is bioxide. So it's bioxide, and then molten cryolite. So the formula for molten cryolite is N3L and then hexafluoro, right? So this is the formula. And then for aluminium oxide, we already know the formula is O3, right? So to predict the reactions at the cathode and the reactions at the anode, first we need to identify the ions being discharged. So we are having for the cations, we are going to have, so we have the cations and the anions. So we are going to have the sodium ion, and we are going to have the aluminium ion, right? And then here we are going to have the fluoride ion, and to have the oxide ion. So this aluminium ion is less stable compared to this sodium ion, and then this fluoride ion is more stable compared to this oxide ion. So mean to say we are going to oxidize this oxide ion to oxygen, and to reduce this aluminium ion into aluminium. Okay, so at the cathode you are going to have the reaction is aluminium plus 3 electrons to give the aluminium metal in the liquid film, right? And then here is the aqueous, right? And then at the anode we are going to have O2 minus to be oxidized to oxygen by giving electrons. So we're going to simply balance here 2, and then here 4, then here gas, and then here aqueous. As simple as that. So these are the equations. These are the equations we are going to have, right? And we now proceed to the next part, which is number E. So number E says a sample of 2.34 grams of aluminium is reacted with 50 cubic centimeters of 2 moles per cubic decimeter of sulfuric acid. So they react according to this chemical equation. So show by calculation that aluminium is in excess in this reaction. So we want to here to find the amount of aluminium that reacted, and then we subtract from the amount we originally have, right, of aluminium. So here we are given the amount or the quantities of sulfuric acid, right? So they react in the ratio 2:3, right? For 2 moles of aluminium we are having 3 moles of sulfuric acid. And then here we are given the volume, which is 50 cubic centimeters, and then the concentration, which is 2 moles per cubic decimeter, and then the number of moles is the unknown. So N is equal to CV, right? So we're simply going to multiply these two quantities. So it's 2 by 50 over 1000, right, to convert it into cubic decimeters. So we're simply going to punch this straight to our calculator, right? So it's 50 divided by 1000 multiplied by 2, and we are going to have 0.1 moles, right? So the amount of sulfuric acid here is 0.1. So 0.1 will give us less, right? So we are going to have 0.1 over 3 multiplied by 2. So 0.1 by 2 divided by 3. So we are going to have 1 over 15, right? So this is the number of moles for the aluminium atom, the aluminium metal, right? So N is equal to mass over mR, right? So we want to find M. So M is equal to, we want to make this M the subject of the formula. So M is equal to N multiplied by mR. So our N is 1 over 15 multiplied by the mR of aluminium. We are going to have 27, right? The mR is 27. So we are simply going to say multiplied by 27, and we are going to have 1.8 grams, right? So we have 1.8 grams reacting, and originally we started with 2.34, meaning to say from 2.34 we only used 1.8, meaning to say aluminium was in excess. It's simple as that, right? And we can now proceed to the next part. We can now proceed to number 8. So number 8 says alkenes are a homologous series of unsaturated hydrocarbons. So unsaturated meaning to say we are having carbon to carbon double bonds. Hydrocarbon we are only having carbon and hydrogen, right? So name the alkene which has only 3 carbon atoms in its molecule. So we start with meth, we go to eth, and then to prop, right? So we are going for propene, right? And then draw the structure of an unbranched and a branched alkene. Show all the atoms and all the bonds in each structure, right? So we're going to give any branched or any unbranched, right? So we're going to have let us say we are having butene for the unbranched, so it's C H, so right, so it's CH2 here, right? And then we're going to have the carbon to carbon double bond, and then H, and then as simple as that, right? And then for the branched, let us say we're going to have 2-methylpropene, so it's 2, right? And then here we have the double bond H, right? And then we're going to have C here, and then H, and then H, and then here we're also going to have the C, H. So for O level, we don't normally want to discuss about the spatial arrangement because this double bond offers the repulsion between the bonds. But for O level, we don't want to normally discuss much on that to explain the trigonometry on this carbon atom, right? What you just need to do is to show the arrangement, to show the appreciation of the presence of these 2 methyl groups, right? And then we now go on to the part C, which says describe a chemical test that distinguishes an alkene from an alkane. So we're going to use bromine water in darkness, right? So we are going to use bromine water where in darkness. So you must include that because in the presence of UV light, both they're going to decolorize bromine. So in the presence, in the darkness, only an alkene is going to decolorize, right? Only in alkene is going to decolorize, and then this one, no reaction. As simple as that, right? And then we now go on to the next equation, which says alkenes are manufactured by the cracking of long chain hydrocarbons. So the equations for cracking, we are breaking large alkanes into low molecular alkene or alkane, right? So we are starting with an alkane. You need to take note on that. We are starting with an alkane being broken down into either an alkane or an alkene or hydrogen gas, right? Are we together? So give 2 reasons why cracking of long hydrocarbon chains is important. The importance of cracking. So we want to break the large molecular sized alkanes into smaller chains which are more useful, right? So the shorter chains, or the smaller alkanes, shorter chain, they are more useful, right? And then we want also to produce alkenes, right, which are essential for other uses, right? We can use them as source of fuels or into the manufacturing of addition polymerization in the manufacturing of plastics, right? Plastics, right? And we can use it in the manufacturing of hydrogen, right? So we can use it in the production of hydrogen gas production. And we are now moving on to the next part, which says compound X contains 85.7% of carbon by mass and 14.3% hydrogen by mass. So using this percentage, calculate the empirical formula. So empirical formula is defined as the simplest whole number ratio. So it is the simplest whole number ratio, right, of atoms present in a compound. Simplest whole number ratio. The definition must include this statement: simplest whole number ratio of atoms present in a compound. It's not just a ratio, it is a whole number ratio, right? So show by your working and also state the molecular formula for X, and it is awarded for 3 marks, right? So first we are going to start by calculating the empirical formula. So we are having carbon and hydrogen, and we are going to write the abundance is 85.7 here, and then here we are having 14.3. We are going to divide with the AR, atomic mass, on the periodic table. So 85.7 divided by 12, we are going to have 7.141666, and then 7, and then here we are going to have 14.3, and we are going to divide with the smallest. So this one obviously is going to be the smallest, right? Divided by 7.14166667. This one divided by the smallest, 7.1, right? So we're going to store this one as A, and we're going to say 14.3 divided by alpha A to give us 2.00, which is simply 2. So the empirical formula is going to be CH2, right? CH2, right? So the molecular formula of X, we are simply going to deduce X here, So we are having butane decane being cracked into two organic compounds, right? So we are having 14, the number of carbon atoms, being equal to 2. Let us say the number of carbon in X is equal to A, or X, 2X, right? Plus 8, the number of carbon atoms in this compound. So we are going to simply solve for X here. So it's going to be 14 minus 8 is equal to 2X, and then you're going to have 6 is equal to 2X, and then 3 is equal to 2X, as simple as that. So the number of carbon atoms is C3. And then we do the same to solve for the number of hydrogen atoms. So we are going to have 30 is equal to 2X, the number of hydrogen atoms, plus 18. So we're going to simply say 30 minus 18 is equal to 2X, and they are simply going to have 12 is equal to 2X, and then 6 is equal to 2X. So it's going to be C3H6. As simple as that, C3H6. So C3H6, right? And then we now proceed to the next part of the paper, which is number 9. So number 9 says ammonia is used to make nitrogenous fertilizers, ammonium chloride, ammonium sulfate, right, and etc. So ammonia is manufactured using the reversible reaction between nitrogen and hydrogen, what you call the Haber process. So you should be able to give the conditions for the Haber process, right? The temperature 450, pressure 200 atms, and we are going to have the catalyst, which is powdered iron. And to explain why the catalyst is going to be powdered, not a solid iron, right? So powdered to increase the surface area. You should be able to understand that. And then construct the equation for the reversible reaction. So we're going to have nitrogen gas reacting with hydrogen gas to give, so this one is a reversible reaction, to give ammonia mean. So to balance this equation, we are going to have a 3 here and then a 2 there, and the equation is now balanced, right? And then ammonia is used to make soluble salt ammonium nitrate, right? All nitrates are soluble, right? You must understand that. Name the acid that reacts with ammonia to make ammonium nitrate. So it's obviously we're going to react with an acid which will give the nitrate ion. So is obviously we're going to react with nitric acid. So this is the chemical formula for nitric acid. So this one is the nitrate ion, right, as you can see. And then the next part says calculate the percentage by mass of nitrogen in ammonium nitrate. So we are having ammonium nitrate. So this is the chemical formula for ammonium nitrate, and you are going to simply add the total number of nitrogen. So you have 2 nitrogen atoms, right? So it's 14 here plus 14 there, and we are going to have 28 divided by the total mass of this whole compound. So the total mass of this whole compound, you are going to have 28, the mass of 2 nitrogen atoms, plus 4, the mass of these nitrogen atoms, plus 16 by 3, which is 48, right? So we're simply going to add this on the calculator, 28 plus 4 plus 48 to give 80. So we're going to say over 80 here, multiplied by 100, and we are going to have 35%. As simple as that, right? So we are now moving on to the next part, which is number C. Nitrogenous fertilizers such as ammonium nitrate leach from the farmland and cause water pollution problems in the rivers and the lakes. Name the process caused by this type of water pollution. So this is what we call eutrophication, right? The accumulation of nitrogenous fertilizers in the water bodies, right? So this is what we call eutrophication. And then explain why this type of water pollution problem is increased when nitrate fertilizers are used instead of other fertilizers. So we said all the nitrates are very, very soluble, right? All the nitrates are soluble. So they are easily leached by rain into the rivers, thereby accelerating eutrophication, right? So we said they are very soluble, so they are going to be easily leached by rain into rivers, right, thereby accelerating eutrophication. As simple as that, right? And we now proceed to the next part, which is number D. So number D says a farmer adds ammonium nitrate to soil. The farmer then adds calcium hydroxide. State the purpose of calcium hydroxide to the soil. So calcium hydroxide, it is a basic compound, or hydroxides. They are going to ionize, providing this hydroxide ion, which will then neutralize, right? So to aid calcium hydroxide is trying to neutralize the soil acidity, right? To reduce acidity of the soil. So we can say to neutralize soil acidity, right? This is the purpose of aiding calcium hydroxide. And then the next equation says extract the equation for the reaction between ammonium nitrate and calcium hydroxide. Use the information in your equation to explain why ammonium nitrate fertilizer is less effective after calcium hydroxide. So we're going to start by constructing the equation. So we are having ammonium nitrate, and then we are adding calcium hydroxide, and then we are going to have calcium nitrate, right? This is the chemical formula, and we are also going to have ammonia plus water, right? So to balance this equation, we need a 2 here and a 2 here, right? And a 2 here, right? So this equation is now balanced. So the question says use the equation to explain why ammonium nitrate fertilizer is less effective after calcium hydroxide is added, right? So calcium hydroxide will react with these ammonium nitrate, or the ammonium ions, to produce ammonia gas. So this reaction is going to remove the nitrogen, right, in the form of ammonia gas. So this is going to make this fertilizer ineffective. Why? Because this nitrogen is going to escape from the soil in the form of ammonia gas, right? Are we together? So we're now moving on to the next question, and we are done, right? So we are done. So always remember to subscribe, to like, to comment, and to share wherever you feel like you need our attention, right? So thank you.